another DraftScience video presentation. So, Pyrrho, as predicted, I mean, as is always the case, I make a comment, point out something explicitly, he changes the subject. So now he's responding to the video I made in Skype, which is not very useful because the Skype conversation was one linear conversation and now it's going off in another direction. But anyway, and it's just not very useful. So I'll read some of that and then I'll give you an explanation of how energy moves in the universe. Okay, a more elemental understanding. And it'll sort of make it understandable why, why it works that way. Why momentum is the man and the kinetic energy formula is nonsense. And it's nonsense again. The history proves it's nonsense. It's not only silly on its face, it's silly as a historical piece of science. The science is silly of its invention, of its existence. Anyway, no, it creates the same amount of energy. The same amount of energy. So we explicitly know the two formulas come up with completely different definitions of energy. We know, I'm arguing, that we're knowing exactly how much energy we're putting in. It's a fixed amount of energy. It's not a continuous force. Let's understand that. Some people don't understand that if I throw a bowling ball into a wagon, it's not a continuous force. Okay, there's one force that hits the wagon. It happens over a very tiny amount of time, and that's it. Okay, it's not a continuous force pushing the wagon. It's a bowling ball that landed. The bowling ball kind of stops, and the wagon starts moving. Amazing. Well, anyway, and different amounts of momentum. So we know that all of these thought experiments start with the same exact amount of momentum. The bullet has the same momentum as the bowling ball. We know that because we use the same charge to move them. All right, the bowling ball is going a lot slower, but the bowling ball is a lot heavier. Same exact momentum. The energy formula applied to the exact same circumstance, the bullet going 300 meters per second, the bowling ball going 6, says they don't have the same energy. The momentum formula says they have exactly the same momentum. They will, however you say it, knock over the same number of pins. They will interact with atoms. If you extract all of their energy quite efficiently, they will give you the same energy back. So if you could find some friction device to stop the bullet, little tiny sticks that you knocked over, you would knock over the same number of sticks with the bowling ball as you will knock over with the bullet. The same stopping force is required because they both contain the same force, because they were given the same force. So instead of paying attention to what the subject is, he's somewhere else. Okay, it's obviously your premise is completely inaccurate. It doesn't describe the circumstance. I deliberately made it so the bowling ball and the bullet have exactly the same momentum. You can't say they have different amounts of momentum because I've established it's the same. Anyway, just because you want to call momentum energy, it's not that I want to, it's that's what Descartes said. That's pretty much what Galileo said. Not insignificant characters, and certainly it's what Newton said. Okay, every way Newton described the motion of every object in space, he described it as mv. He didn't use mv squared. So let's understand, none of Newton's celestial mechanics has any mv squares in it. All right. And because you want to call momentum energy, as if, like I said, the word energy wasn't invented until Thomas Young threw it on there. So yes, everybody used different terminology, but we know if there was such a word as energy, Descartes would have used it, okay, Voltaire would have used it, Newton would have used it. All right. There are two different, we'll throw in this little extra shot. Just because you want to call momentum energy, it doesn't matter, you get confused. So what's the confusion? You have two formulas. They give you completely different answers. How can you call momentum not energy when everybody knows it's energy? The football player, 300-pound football players coming at you at 5 miles an hour. A 100-pound football players coming at you at 100 miles an hour. Everybody on Earth can figure out one of them has more energy. The momentum of the 300 pounds is a lot more of a problem for you to deal with than the momentum of the 100-pound guy. They're moving the same speed. One of them has less momentum in that case. Less momentum means less energy. If I put a generator on it, there are wheels. If I put a generator on, I'm going to generate more power out of the 300-pound guy going 10 miles an hour than I'm going to generate out of the 100-pound guy going 100 miles an hour. Same is true for a car or anything else. It takes more energy to move the bigger mass, and it takes more energy to stop the bigger mass if you're going up to the same exact speed. That's the truth. Momentum is energy. All right, there are two different quantities. How can there be two different quantities? We're talking about one quantity. How much trouble you're in. Okay? We're just talking about how much damage, how many cells, how many microbes, how many things it's going to squish. It's squishing power. We're just saying how much squishing power does the object have. There's two formulas to decide squishing power. Your formula says things going fast squish more stuff. My formula says no, it's about how much mass you have and how much velocity you have, and the two things are equal in terms of deciding how much you're going to get squished. All right. There are two different quantities. No, there aren't. Both calculated from mass and velocity. So he says they're two different things somehow. Somehow energy is something and momentum is something different. Somehow kinetic energy is something, and somehow momentum is something different. How can they be different? They're about how much movement you can cause, how much heat you can create, how much anything you can have happen in the universe. It's about how much you can make happen. All right. You just can't unravel their bullshit. They're just so lost in it. Anyway, they are both legal to calculate, like you can add and multiply whatever the fuck you want. So I don't even know what the use of that was. But to say they're both legal, that's not their history. The explicit history was to replace the idea that momentum gave the right answer. The argument was, we don't like Descartes' figuring. And it was mostly about Descartes at first, then it was Newton. Okay, so again, there's no doubt. I mean, they explicitly mentioned Newton, okay, in the argument. So they were attacking Newton. I mean, it started with Descartes, and they were attacking Newton. All right, the whole idea was to one-ups him, okay, because they felt like weak scientists, Newton was the man, and they weren't. And they wanted to do something about it. So they invented new physics. And it was junk. All right. So anyway, this isn't about anything legal. It's about what the truth is. What gives you the right answer? Anyway. And you say, you will die if you use this to navigate to Mars. So, and then he says, they have used it to navigate to Mars many times. So he says it overtly, that the physicists that, land the little rovers on Mars, they think if they throw light things fast off their spaceship, like garter belts and panties, they throw all their underwear off the spaceship really fast. Okay, that's going to get them more, power to move than if they throw, bowling balls. They chuck a bowling ball out the window, that ain't going to get them nowhere, okay? That's pussy shit. You don't get anything for that. But throw your underwear out the window, oh yeah, yeah. Get your underwear up to 50 or 60 miles an hour, oh yeah. Yeah, that'll give you huge power. Because that's so much more energy when it doesn't. Same momentum. Anyway, so he says they've used it, but he won't prove they've used it, okay? There won't be anything in the calculations of when they're calculating thrust, the little bits of shit they spill out to move something, they're calculating exactly its momentum. All they care about is how much mass and how fast did I move it, okay? That total, that's all that matters. They don't think because I move it faster, that I push it out faster, that I'm going to get anywhere by creating light things that go faster. They think heavy things going slow is just as good as light things going fast. Okay. So again, we're just not going to get any proof that NASA is stupid. They're not going to show me the NASA doing these wrong calculations and landing on Mars. It just doesn't happen. Okay. What the hell are you thinking? Yes, you mean how dare I? Well, I have some reason to say it, right? Because we know that there are NASA engineers who actually landed men on the moon, and they said we didn't use anything but Newton's mechanics. They've overtly said it. That's all we ever used was Newton's mechanics. And again, this is Leibniz mechanics. This isn't Newton. This energy formula has nothing to do with Newton. Newton never said, yes, convert F equals ma into, yeah, put the velocity twice in your equation. 2 V's. VV for Viva Vista, right? VV, right? Oh, that's coincidental. The living force, double V. Anyway, if the current rocket physics is a hoax, so again, it's not about it being a hoax. It's about the fact that when push comes to shove, the NASA engineers use the formula that's going to get the right answer. Okay, then there are all the successful space missions using it hoaxes. Are all the successful space missions using it hoaxes? So again, you have no evidence, you will provide, that when they're steering the little lunar module to get to the right position to land on the moon, that they gave a shit about your silly extra energy you can get by throwing light things. No, they don't care about that. The only thing that matters is the weight and the velocity. So when they shoot some molecules out, all they care is how much they weigh and how fast are they going. That's it. No double speed crap. Mass is just as important as velocity to a NASA engineer. All right. This is an elaborate flat earth argument. So again, until you show me evidence, it's really not. Now, we know there's a ton of evidence against a flat earth, right? Satellite photos, all kinds of things. So far, nobody's shown me a single shred of evidence showing you collecting this extra energy that exists. So you've never collected this extra energy. You have no experiment demonstrating it. Zero. You won't show me one single experiment. You won't show me a NASA engineer doing the calculations with mass times velocity and getting the wrong answer. You won't show me the NASA engineer saying this formula doesn't work. Momentum doesn't work. I can't use momentum to steer my spaceship. That would be silly. I'm not Newton. I'm not an idiot. You won't show me a NASA engineer saying momentum doesn't work. Seriously, Pyrrho, what the fuck? You really think there's a NASA engineer who says Newton doesn't work? Okay. So there you go. Well, I shouldn't even read the rest of this crap. It's just crap, right? This is just a distraction. Okay, here's what historically overtook momentum as our idea of energy. So he doesn't know any of this history, right? And I've researched it extensively. So I bet he never even saw the Einstein PBS video, where the whole middle section is a dramatization, with a very pretty woman, by the way, playing Lady Chatterlette or whatever. I already played it on this channel, okay? I already directed you to the history channel. The woman does the history videos, and she did the whole video on it and showed it too. It's very nicely portrayed. The Voltaire thing, the lady thing, the little clay experiment thing. It's all right there. That's the real history. That's how bad the real history is. They went out and quote mined the experiments. So these Germans and French people, they quote mine the experiments to find the ones that look like what they're saying. 4 times the energy, twice the velocity, 4 times the energy. But that's all they do. They just quote mine. All right? They didn't sit there and say, well, let's try springs. Let's try all these different objects and see if we can duplicate this effect. And it's just that obvious that it's garbage. It's junk. And then the very fact that Young is the guy who invented the word energy, and Young famous for the fake double slit experiment, and that's a fake. I mean, his drawing is a fake. Okay, you can't put the wave centers in the middle of the slits and get anything close to a right answer. It'll never give you the right answer. So more fraud, more phony, more just really bad science, okay? It's just bad science. All right, so anyway, let's continue. Here's what historically overtook momentum as our idea of energy. Energy besides kinetic energy, how does this even make sense? Energy besides kinetic energy, one, and the desire to make steam engines, two. I mean, it really has nothing to do with the fact that they finally figured out where their friction losses go, creating heat. That's hardly something in dispute here. I'm not claiming that heat isn't something you do create when you have interactions. I'm saying that you clearly can control how much heat you create. But I never said heat wasn't energy. Those are losses. If you're making heat, I'm moving 30 miles an hour. So if something's moving 30 miles an hour through space and there's no friction, are they still making heat? Is that your theory? They're still hot? They're making the empty space hot? You know, obviously we already know that heat losses come out of your momentum. You don't get to keep your momentum and start fires on the floor. You know, I can't have friction, start a fire, and then say, look, I keep going 30 miles an hour. I don't slow down. It's amazing. I get to keep my momentum, and I can make fires. So I'm sure people who were making steam engines knew they can't make heat for free. They have to put a whole bunch of wood in the fire. Yeah, it's a real pain in the ass. You have to make the heat out of something. Shit. And, just amazing. This horse shit. All right. In the latter, you want to know what work you can get done applying forces to heat to masses. All right, forces and heat to masses and boilers. Yeah, and obviously heating up a boiler is a lot different than just banging a kinetic object into another kinetic object. So exchanges of momentum or accelerations can happen very, very fast, or they can happen very, very slow. Like gravity, you can apply the force continuously. You know, you just have a kicking machine. Gravity is just a kicking machine, right? It's just doing this. Kick, 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 kick. The idea is the longer you're in the kicker, the more time you spend in it, the more energy you collect. The less time you spend in it, that is, if you're going really fast into the kicking machine, they don't get anything out of it. It doesn't kick you very often, right? So it's just about how much time you're in the continuous force. But we're really not talking. Trains aren't continuous forces. They already have their momentum. They're not getting momentum. They're not continually being pushed. They already have their momentum. They have the energy in their motion. And we're just talking about how much there is. And the simple argument is I can inverse masses and velocities and I have exactly the same amount of energy. All right. You get done. Let's see. Applying forces and heat to masses and bodies. Yes, so again, there's no argument that a heat is a form of energy. Okay. That leads to the joule, says you. Newton's apple leads to the joule, right? But the interesting question is, the thing you can't find on the internet, which I thought was hilarious, is I can't find the experiment where they actually drop an apple on a scale and see how much it deflects the scale. You know, because that would be very interesting to see the exact thing, right? So you have a Newton, which is the weight of an apple. And then you have a joule, which is the weight of an apple after it fell a meter, right? So why don't they just measure the joule by just dropping the 100 grams, drop it, okay? And then we can see how much it deflects the scale. We can see how much a joule weighs, right? That would be very useful. If we know the weight of a joule, then we can do this easy conversion here. We can just convert all this into weight. Because really measuring the weight of something is exactly the same as measuring its momentum. I've already tried to get you to understand that over and over again, but it's exactly the same thing. If I stand on the table and jump on a scale, I'll weigh 800 pounds. That weight is telling me my momentum. And then if I'm not jumping on the scale and I just stand on the scale, it's telling me how much gravity is pushing me continuously, because gravity is a continuous force. So I'm getting a continuous reading of how my momentum is changing. My momentum is being, gravity's pushing me down, the Earth's pushing me back up. The gravity's pushing me down, the Earth's pushing me back up. So I'm oscillating, okay, and that oscillation is my weight. Okay? But it's real momentum. I really am moving. And that's why the scale moves, is because I'm moving. And if I move with more momentum, more velocity, the scale will read it. So we can measure momentum by merely putting things on a scale. Make them bang into a scale. The scale will tell you how much they weigh. Now, the problem with measuring the bullet is it makes a hole through the scale, so it bends the scale. There's all kinds of things. So you have to try to catch the energy more gracefully to measure its momentum. But certainly, if we're measuring the momentum of a bowling ball, yeah, we can just roll it into the scale and it'll tell us how much the bowling ball weighs in that direction. That's its momentum in that direction. Okay. W equals FD. So this is just more made up crap. Well, I'm going to say the force isn't something you can define. You can define its velocity. So why don't you just stick with that? We know what its velocity and its mass are. So we can say if that's the force, and I'm perfectly fine with doing that also. So energy equals force. That would be a good thing, a good comparison, a good thing to squish together. So you could just say energy, okay, times distance. Now he says times distance. No, it's times time. But it doesn't really matter. Neither one of them are important when you're going to calculate how much work the object did, because the fact is the work was in moving it or stopping it. That's how you measure the amount of work it's capable of doing. So if it takes a certain amount of energy to make something do something, the work is in the bowling ball rolling. I did the work. I know how much energy it took to make the bowling ball roll, and then certainly I can figure out how much energy it stops to the bowling ball rolling. So I know exactly how much work it did, and it's exactly equal to the force I had to apply to make it do something. All right, anyway. That is the description of a finite steady rocket bursts. So W equals FD is a finite steady rocket bursts. There's a total mass. There are little particles. There's a total mass to the little particles, and then there's a velocity to the little particles, and that's the only thing that's going to define how much work you did on the particles and how much equal and opposite reaction you're going to get. So they keep reciting Newton's laws. Well, that's one of Newton's laws, bozo. If you say it's 300, because you threw a tennis ball out this side really, really fast, we'll just use the bullet again, a really fast little tiny bullet out this side, and you say it has 300 times more energy than the bowling ball that went out the other side, you're stuck with your own equal and opposite reaction law. You have to concede that, okay, this side's going to move from 300 to 6. Obviously the spaceship's going to go almost sideways. All right, it will go sideways. It'll go all the way around until it gets almost back to 12 o'clock. The disproportion is so substantial. All right, you turn on the thruster force for a given distance. So again, this has nothing to do with any given distance. Doesn't matter how far the force goes. It doesn't matter how far the tennis ball goes or the bowling ball goes. We already know its velocity, and nothing's going to stop it. So frankly, it can go forever. Distance has nothing to do with this analysis. Nothing. You turn on the thruster force for a given distance. You put W equals F times D. So again, this is just gibberish. It doesn't mean anything. This playing with your little symbols and your little, big F's and big W's, and it doesn't mean anything because you don't get to anything elemental. What is the nature of the energy? Okay. That helps moving fucking trains around, says you. Okay. What helps moving trains around is momentum. All that's ever going to matter, football player, train, bowling balls, all that ever matters is how much mass and how much velocity. And the mass isn't half as important. It's just as important as the velocity. The concept of energy has units of mv squared. There's no such thing as a unit squared. So it's just absolute bullshit on its surface. A joule isn't a squared joule. I mean, you can't have a squared piece of dynamite. There's so much because it has a certain mass of the chemical. There's no squaring. It's an amount, period. There's no mv squared, of joules. The real problem is you think the foot is the same thing as a square foot. Yeah, I think there is a huge difference between it, but I'm just saying I know that units are 100 grams isn't a square gram. There's no such thing as a squared gram. There's no such thing as a square pound. There's a pound. It weighs a pound. It's a pound of mass. There's no squaring of your mass. Otherwise you'd get it. There's nothing to get. There's two different answers for the same question. Oh, here's some new shit. Fuck. Anyway, just the whole video is going to be this, and I wanted to do the other thing. But anyway, you need to answer. No, I don't need to answer. You didn't answer my questions. You haven't answered the paradox at all. The paradox is right there in front of your face. You're claiming you lost a whole bunch of energy in the train example. Half the energy was lost, and you won't show me where it went. The tracks didn't catch fire. I mean, anyway. Is it somehow a hoax or cheating or wrong in any way to calculate the force applied over distance? So again, he keeps talking as if any of these experiments have anything to do with force over a distance. None of these are gravity. This isn't a gravity equation. Shoving crap out of your spacecraft to turn it has nothing to do with gravity. Nothing. It has to do with how much energy you're producing by getting rid of stuff at a velocity, by disconnecting it from you at a velocity, taking it from your ship and throwing it out at a velocity. Okay, it has nothing to do with any force applied over a distance. The force already exists. The bullet almost instantaneously acquires its velocity. It acquires it very, very, very fast. Before it gets to the end of the gun, it's already going its huge, giant velocity. This isn't about applying any force over a distance. Anyway, by multiplying the force by that distance over which it was applied. So I mean, the application of these forces is so tiny in distance, it could mean nothing to anybody rational. When the two trains hit each other, the amount of any kind of deformation is so slight and so infinitesimal. The amount of deformation in the Newton's cradle when it bangs into the the other balls, there's no distance, there's no force over distance equation there. The force is applied in an instant, in a little tiny shred of space. Okay, so anyway, distance by multiplying the force by the distance over which it was applied. So that formula will not get you the right answer. I mean, if I use that formula just to do the 100 grams, right? I have 100 grams, and I'm going to drop it a meter. Know what answer I get? I end up with less weight when it hits the ground if I use his formula. If I use this idiotic formula where you're measured by the height, times the distance, you don't get the right. You get times the gravitational constant. You don't get the right answer. You end up with a number 0.98. How could I have less than what I started with? So, anyway, I am let's see, applied over a distance by multiplying the force by the distance over which it was applied. Okay, so again, we know this has nothing to do with any of these scenarios. A little charge in a gun goes off. The applied distance of the force is so tiny it can't make any difference. Bowling ball bullet leave at velocities. Not affected by any of this nonsense. We know they have a velocity when they leave. We can watch their velocity. We can calculate it. We can put a little timer, a little photo detector, and we can see exactly how fast they're going. We can measure their actual continuous velocity. This is not about acceleration. It is about velocity. It's about momentum. Momentum isn't about accelerating bodies. It's about ones that are already accelerated. All right, anyway. Am I allowed by you to take my 1G thrust rocket? So whatever a 1G thrust rocket is, right? Doesn't mean anything, because we know to get to that 1G, it's going to be a certain number of pieces of matter, real mass, and you're going to have to give the real pieces of mass velocity. And that's all that's going to matter. How much mass How much velocity? Both of them equally important. By you to take my 1G thrust rocket and turn it on a while. Well, if you're going to turn it on a while, if you're not going to, then you still have to calculate the total number of mass units you ejected and their velocity. So turn on as long as you want. And that's going to be a total amount of energy that you have created. If I did that to the train, then the train's going 10 miles an hour. Well, then it has 10 miles an hour's worth of momentum. I've given it its momentum. Who cares what accelerated the train? It's totally irrelevant to the question of how come the 10 mile an hour, 5-ton train has twice as much energy as the 5 mile an hour 10-ton train. Your math says one of them has twice as much energy. They have exactly the same momentum. How can one of them have more energy? It won't take more energy to stop them both. It'll take exactly the same energy to stop both of them. If I'm standing there pushing, the 5 mile an hour, really twice as heavy train is going to be just as hard for me to stop as the 10 mile an hour 5-ton train. The same exact amount of work I will have to apply to stop both trains. You say one train has twice as much energy as the other. That's the paradox. Will you get to the point? Will you explain to me how the same stopping power works when the two objects are supposed to have completely different amounts of energy? I mean, that might be the best, best way to phrase it. That might be the best way to state the question. How does the same stopping power, me pushing, work on both objects if both objects are supposed to have different energies? All right. Travel a mile and say applied 1G times 1 mile equals 1G mile. So again, you're just playing games here about how you're going to add up what 1G equals when we know the G equals what the mass is. If I'm in gravity, it matters on how much mass I have, how much I'm going to weigh. If I'm a small object, I weigh less because I can absorb less of the force. The continuous force isn't 1G, okay, in the sense that we're both collecting the same amount. It's a rate that it's coming down, and we have different size capacity to collect it. So the heavy object collects more of it per second. That's why it drops with more energy. That's why it hits the ground with more energy. It's because it collected the energy. And it collected more because it had more matter to collect it with. It had a bigger sail to collect the gravity wind. Anyway, this is no point. And that is why it's moving now, afterward. And that is why it's moving now, afterward. And why it's moving a particular speed now, afterward. So there's no way to make that make any sense. So again, this has nothing to do with acceleration. This has to do with just transfers, the most efficient transfers possible, and it just has to do with how we calculate how much energy the object has. And I'm arguing the 300-pound football player going slow has just as much energy as the 100-pound one going fast. And he's arguing, no, they have very different energy. The 100-pound guy has a lot more energy. A lot more. Twice as much more. In the example of 300 and 100, guess what? When I give them the same momentum, their argument would be is that the light player has more than twice as much power to knock you down than the big fat guy going slow. More than twice. So just think about that in your head. And if I made him even smaller, I made him a midget. So now he's down to 50 pounds. Now he has like 4 times as much energy, capacity to hurt me as that big giant guy. That's what they believe. I make him into a Tweety bird. Now he's really trouble. I make him this tall and he weighs 7 ounces, but now he's going, 200 miles an hour, which might be a problem. It might dent me, but it's not going to knock me over. Anyway, just, yes, from everybody's appearances, it doesn't look like an elephant's butt falling on a chair has the same energy as a bullet ripping somebody's brain to pieces. But if you calculate how many atoms are going to get disturbed, then you can understand that, oh yeah, the bullet's really small and it only has a few atoms in it, and those atoms can only hit a certain number of atoms, and they can only exchange the energy. And so obviously that little high energy and little package, yeah, big package, low energy, but it's got a lot of spreading power. I mean, it can spread it and spread it and spread it. It's an ancestry tree, really. And you're just looking at it two different ways, right? I mean, I start off with Adam and Eve, and I end up with people. They're just trying to say that they're comparing the charts in different places on the chart. But the charts are all the same chart. It's the same idea, the same energy. And if you look at it, you know, with them out of shape, it'll look like, oh, there's more people in this ancestry than there is people in this ancestry. But it's all the same. It's the same. You just have to. They have to be lined up. Momentum tells you they're the same cones. Yeah. Well, I'm trying to think of different ways of making this understood, but so anyway, that was just horrible. Yeah. So that's a horrible response. So who knows if Pyrrho, like I said, I mean, it really has to be talked through, because I have to be able to nail him on each one of these points. Does he really believe a physics that was really the only experiment they did, essentially, was dropping steel balls into clay? And they decided what something was based on that one experiment, where Newton had hundreds of different experiments with different objects. Galileo, these people bang shit into stuff all over the place, all the time. If they would have noticed if momentum didn't work. They would have noticed. Alright, well, I'll take a break. Yeah, that's what I'll do. See if it's... Maybe I'll just leave this and then I'll do the other thing in a separate video. I've only done 3 videos today, so what the hell, 4th, who cares? Because that took much longer than I thought it would. Well, let's see if there's any other comments to deal with. Well, maybe I'll take a break and then I'll do some more comments. Alright, I'm back. Alright, so this is, I don't know, John Ham, you know, well, probably just a troll of some kind. Anyway, explain, it's all caps. I mean, this is just like so juvenile. And somebody gives him thumbs up for an all caps crap, right? It's got to be himself, no doubt. Explain power of space vacuums as compared to ocean depth pressure and its effects on space vehicles. Well, there's no space vehicles underwater, but anyway, obviously one pressure is going in and one pressure is going out. I mean, you know, the problem in space isn't keeping the space out, it's keeping your pressure in. Okay, the damn thing wants to blow up. Okay, it wants to explode out. The thing underwater wants to explode in. Okay, two opposite things. So I don't even know how I could ever compare the two, because they're two opposite sources of pressure. But what would they have to do with anything? They don't make you move. If I go into a vacuum, the vacuum's on both sides. I don't want to blow up more that way than I want to blow up that way. So I don't even know. It just couldn't be less on the subject, right? No, it really couldn't be less on the subject. I don't think that has anything to do with momentum and kinetic energy. So, fuck off. Jesus. All caps. Oh, that was so important, right? Didn't we all need to have me explain that the pressure underwater is pushing in and the pressure up in space is inside your vehicle, providing you with an atmosphere to live in? Yeah. Oh, no. You know. Yeah, it's vital that I explain that. Anyway, this horrible name guy. Momentum is more appropriately applied to things that are at constant velocity. Yeah, they already have their velocity, but they're not being constantly pushed. So if you're going to apply a force and say, ooh, it has a constant force pushing it, the train doesn't have a constant force pushing it. The whole analogy here is these are two trains that have no new source of energy. All right. Constant velocity, or as a tiny instantaneous snapshot of things that are accelerating or decelerating. So again, that was never a condition of Newton. It wasn't a condition of Descartes. It wasn't a condition of the conversation. The conversation was never about when you have motors on things. The conversation is just about how much does something that's moving, how much energy does it have moving at that speed. If it impacts a tree right now, Yes, how much energy can it deliver? Not 5 miles down the road where it lost all its energy. We're talking about something with an explicit amount of momentum, and we're saying what happens when that momentum hits something. Oh, anyway. I mean, it's just, there's just no point, right? I mean, it's just, or as a tiny instantaneous snapshot for things that are accelerating or decelerating. So again, it just doesn't have anything to do with the entire invention of this formula. It was not invented this way. This isn't what it was. It was called the living force. It has a whole history, and this has nothing to do with that history. That is why it has the term moment in it. Doesn't matter. The term is that it equals something that means something. That is, if they had the word energy, they would have said momentum energy. Just like you're saying kinetic energy, they would say momentum energy. It's a definition of something's energy. And the fact that it's so glaringly true, in the sense that every single thing that happens in the universe involves momentum exchanges. Momentum goes into atoms. Atoms are momentum when they hit another atom. It's always about momentum. Everything functions based on it. It is the clearest line between energy and any other secondary word in the universe. The cleanest line is the line between energy and momentum. Anyway, kinetic energy is not about the constant velocity of a thing. So he's just ignoring the entire subject. That's not the history. The history is about objects moving with velocity and mass. And the fact is, that's what it's about. It's not about acceleration. It's not about any other kind of bullshit. It's about things moving with speed that have mass. And what is the significance of that? Or a particular moment. So again, just more nonsense. Of course it's about the moment of impact. It's about what can be delivered. Again, if I swing a pendulum, I don't, and then I wait for the pendulum to slow down and then it hits a stick. I don't say, well, let's see what it was when it had its original momentum, when it was swinging way up here, and I'll calculate that for no good reason. We already know the rules. When I put the stick in to stop the pendulum, we know that each time it's going to be a different amount of momentum it's going to have. The original amount is going to be high. The last little bit is going to be low. So this is just jargon. I mean, it's not even jargon. It's just uselessly convoluted distraction. Kinetic energy is not about the constant velocity of a thing. When every one of these experiments is about something with velocity, a constant velocity, or a particular moment. And everything about these experiments is the moment of exchange. So there's just no point. It is a exaggeration. So this point of saying exaggeration, so you must be conceding then exaggeration is a bad thing. You don't want exaggerations in your science, right? Okay, so we know that there's something wrong with your formula then. Okay, anyway, it is an exaggeration of the total energy needed to overcome inertia. So again, there's more of this nonsense that inertia has to be overcome. The bucket can't move until you pour, the bucket can't have something in it until you pour something in it. You can't have weight. And, if I put a bucket down and I want to weigh the stuff in it, I can't weigh the stuff in it until I've put it in. The bucket's not saying, please don't put anything inside of me. No, it's just saying it's going to take you time to pour the crap in. All right? The fact that it takes time to pour energy into something has nothing. There's no inertia. There's no will not to move. There's the will to be forced to. Things don't move because you say move. You have to force them to move. They're not stopping you from forcing them. They don't have any shields. They're not locked to the ground. They're not doing anything to stop you. They're just saying, I'm not moving until you push me. There's no inertia. There's no resistance to moving. Anyway. And this is just a huge change of the subject again. The subject is, clearly the two equations say different things about the two trains pushing. Two trains are coming at me. 10-ton train going 5 miles an hour, 5-ton train going 10 miles an hour. I'm going to stand there and push it, stop it, drag it to a halt. You're saying it's going to take me forever to stop the light train going fast, it's going to take me at least twice as long. It's going to take me twice as long to stop that train. I'm saying, nah, they're both going to stop. I apply the same force, they're going to stop. All right. Same energy, same number of punches. If I have a little punching machine, take the same number of punches to stop the light train going fast as it's going to take to stop the heavy train going slow. Same number. All right. Where was I? It's an exaggeration. Inertia to reach some velocity starting from zero or a relativistic zero. So again, all this is totally irrelevant if already in motion, which everything is. Yeah, we've already discounted. This isn't about trying to assess which object has which vector of the opposite motions. We're really just saying that we know they're not the same motion. The momentum of the standing train could be 5 million miles an hour in some direction. Who cares? Because both of them are going that direction, so we don't count those. The directions where they're going the same place, the directions they have the same vector of momentum, we're not counting. So we just don't care about any vectors. You know, we just care that the two of them have opposite vectors. After inertia is overcome, so he's just so full of shit. It takes very little to keep something in motion. Well, apparently it takes a lot when you really think about it. Trains slow down pretty fast. Cars slow down pretty fast. Pendulums wind down very fast when you think about it, right? If I do the pendulum thing, I'm probably only going to get 50 swings out of it, right? Maybe 50. So if you do the math, that means I lost 2% on each arc, you know. Each arc is 2% loss in the momentum. All right, anyway. Where was I again? Reach the velocity starting from zero to a okay, so this isn't about relativity. After the inertia is overcome, it takes very little to keep something in motion, aside from air friction losses, etc. Yes, so those can be substantial. But anyway, it's all in the first part of the scenario. So he's apparently going to get to the scenario. Well, that's good. Where inertia is being overcome by the force. So again, there is no thing to overcome. It's just you having to dump your force into it. There's no inertia. The wagon isn't stopping the bowling ball from falling into the wagon. There's no inertia. Okay? It just takes time for the bowling ball's force to be spread across the whole of the wheels of the wagon. It takes a while for the bowling ball force to get to the wheels of the wagon. And Newton's cradle, right? Newton's cradle, it takes a little while for this ball to fly out. And the little while is the speed of sound in steel. You know, the speed of sound in steel is what has to communicate the energy to the ball on the end. So the momentum is moving at the speed of sound in steel. All right. So it takes a little bit of time. But so what? We know that it does it very efficiently. The energy from one ball goes very efficiently into the other. All right. Keep something in motion. It is all the first part of the scenario where the inertia is being overcome the force and there is acceleration. So again, this is just all crap. It has nothing to do with these transfers, nothing to do with these scenarios. The premise of the scenarios are that I completely transferred, or 99% of the energy was transferred. I transferred 99% of the momentum. So the acceleration problem is already over. We're done with accelerations. We decelerated one object and we accelerated the other object. That's what happened here in all these scenarios. So the acceleration has nothing to do with this problem, because we've already established it was a relatively efficient acceleration. The kinetic energy is the whole curve from relativistic zero to final velocity. So that can't mean anything to anybody rational. Relativity has nothing to do with this. Oh, this is just such jargon. And look, he typed all of this crap. This evasive crap. Totally ignore the history of the formula. Ignore its overt paradoxes. Just ignore the paradox and keep talking this crap. You can't compare this to any particular moment or the moments after the final velocity has been reached. Of course you can. It's all about the inertia. No, there's no inertia. The objects are already in motion. Oh, it's just too pathetic. It's all, I have two different trains. One of them weighs twice as much and is going half as fast, and one weighs half as much and is going twice as fast. It's two different trains. You say they have different energies. I'm saying rationality says they have exactly the same energy. How does this have anything to do with relativity or any of this horse shit? You hunk of crap. And I'm saying clearly, I'm overtly telling you clearly, the same exact amount of force will stop both of them. Because they have the same energy. Your formula is garbage. Okay. In addition to elastic movements, they're not 100% efficient. There is intermolecular slippage and bonds releasing. Again, we went through all this stuff. And I'm conceding, yes, that's the reality. It's hard to make a perfect exchange, but you can have a 99% exchange, can't you? So if I do a 99% exchange, that means 1% of the energy went into the environment somewhere and was lost to slippage, and the energy didn't go the right way. That doesn't explain where half the energy went, loophead. And it certainly doesn't explain why the heavy train going half as fast has half as much energy as the fast, lighter train. It's not going to explain how that's possible. Okay, the slippage may be locked into the structure without expressing free heat, but it still takes energy to do this. He just goes on and on with this nonsense. Yes, it's more than you think. What are we talking about? Ballistics tests can measure water temperature and see this in action. Exactly. So if we just did the right experiments, right? Like I said, they cut the French guy who did all those kind of experiments. They cut his head off, right? So if he was still alive, he would have done that with the clay, and he would have measured the heat, and he would have said, "Oh, there's your problem." Okay, the slow object made the clay a lot hotter than the faster object. He would have pointed out where the energy went, why there's a differential in that particular experiment, and the total energy you'd get to. So the whole point is the bullet going into the water tank, or me dropping the bowl, me thrusting the bowling ball into the water at a half meter per second. If we do that experiment, right, we have a tank of water, we allow the bullet and we have to account for gravity, so and obviously it's not going to give the bowling ball much more momentum than we're actually talking about in the experiment, so it'll work out pretty close. We just hold the bowling ball the distance that'll give it a velocity of 6 miles an hour, whatever it is. So we have the bowling ball going 6 miles an hour, 6 kilometers per second, no, 1/2 of a kilometer per second. And we have the bullet going 300 meters per second into a tank of water, and let's collect the heat, right? So we do that experiment. That should be a pretty good experiment. It'll tell us how much energy there is, right? So that's a good one, right? Because it'll prove the bullet doesn't have any more energy than the bowling ball. Do you believe that the bullet will factually have more energy? Now the only trick is the bullet's going to be hot from the gun barrel, but it went through the atmosphere, so it might have cooled down by the time it hits the water, so that might not be an issue. You're comparing apples and oranges. They're not apples and oranges. They're clearly two formulas that claim to be the Olympic gold medal winner. They both claim to be the same thing. I mean, this is idiotic, especially when we know how important momentum is in terms of all kinds of nuclear functions. To pretend these are competing definitions of energy. For you to use this crap that somehow momentum doesn't mean energy is just absolute nonsense. The momentum is best viewed as a snapshot. So again, it's not a snapshot. It's just bullshit. It's just bullshit. Kinetic energy is the same snapshot. It's the same mass and velocity. The only difference is that they're squaring it. There's no some other variable in this equation. There's just a 1/2 and a squared on the velocity. The same two components are in the frickin' equations, mass and velocity. You're only taking two concepts. I could call it spin and Heisenbergness. It's two concepts, velocity and mass. There are only two concepts in both formulas. You can't play this game that there's some third concept. There's no third concept. There's just them saying velocity is more than twice as important as mass, when it isn't. You're comparing apples and oranges. The momentum is best viewed as a snapshot or constant velocity thing. It's just too stupid. No. They're both descriptions of how much energy the object has. and kinetic energy is an integral is integral of momentum. Snapshots over velocity. Well, then why would you square the velocity? No, it doesn't make any sense. The 1/2 factor is to take the assumed linear response to get its average. Oh, just mush. That's not how the formula was invented. So again, the first 70 years of this formula's life, it was just mv squared. There wasn't even a half. So it was getting the answers really, really, really incredibly wrong. And they didn't even notice. It was mv squared. They were getting huge numbers for energy compared to momentum numbers. Gigantically huge. And at least later they put the 1/2 in, it saved it a little. But it still doesn't fix it. Because it's stupid. There's no reasoning for it. There's no good reason to believe it has any validity whatsoever. It has almost zero experimental evidence backing it up. All the experimental evidence indicates momentum is correct. All the experimental evidence is that everybody knows if they're a quarterback, they're just as afraid of the 300-pound guy going 10 miles an hour as they are afraid of the 150-pound guy going 20. And that's the truth. Okay. We won't bother with William for now. I'm sick of it. Oh, this is the one I already responded to. So blah 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 blah. Oh God, it's just terrible. I didn't. It's not like I expected otherwise, right? I mean, I pleaded in the video for any of the people who really, come on, you can type the words. You can't 100%, right? Can you type these words in the comment? You 100% transfer the momentum, and yet you lost energy. So 100% of the momentum goes from object A to object B, but I lost half the energy. You can't all admit that's a nonsense. That could never happen in our physical universe. You can't admit it? That when physics girls said it, it was ludicrous and stupid? That it was just ignorant nonsense? That it's not good physics? It's not reasonable physics? It doesn't have anything to do with being scientific. It's absolute babble. You can't 100% exchange the momentum and then say, I lost half the energy. There's no way to draw that. So who knows? Maybe I'll make another video. We'll just see. Because I really want to do the deeper science. The deeper science is basically just going to show you there's a bunch of energy in things, right? There's movement inside of objects. Right now, my stuff is moving back and forth, back and forth. And the only stuff energy can hit in me is the stuff actually going out of me. The stuff moving out of me is the stuff you can hit. And when those collisions happen, it means the piece of energy goes this way, and the piece of energy that hit it goes that way. It reflects. But the reflection really is just a continuation of the one that was coming towards me anyway. So that one doesn't count. The reflection doesn't mean anything because it was already one coming for me. And the reflection is just it continuing, right? There's a thing going this way, and then something hits it and reflects. Well, that's basically just continuing something that was already happening, right? So that's nothing new. That one was going to hit me anyway, right? I didn't stop it from hitting me because essentially I got hit by it. The one that changes is the object that expelled this thing, got rid of its heat. All of a sudden its heat's coming back at it again. That's the one that's important. Anyway. So it really is just, you have to think of every situation as things are excreting energy, okay? And all you're saying is that I'm going to explode something and I'm going to excrete more energy. So it can never really reflect to something else. You can only excrete it in the direction. So both objects have to get hit by the same amount of bits. I have an explosion. The explosion has to go equally in both directions. So whatever's over here, the bullet, has to go, it's going to collect a lot of that stuff. And whatever's over here, the end of the gun has to collect the other half. And there's no way to really make the stuff on this side go to that side. You really can't. Anyway. I'll have to surrender eventually. I'll just have to say, fuck it, I can't talk to human beings. because they're insufferably religious and crazy. They don't care about logic. They don't care about facts. The history, I mean, again, the history is so bad on this subject. Again, if you just watch that video, watch the Einstein video, go find the Einstein PBS video. And right in the middle, they're doing the squared thing. And so they have a whole little 5-minute portrayal of the whole French MV squared bullshit. It's right there. And they don't even explain the 1/2 part. Right? They don't even show you the fact that they didn't have that 1/2 on it yet. Okay? It just shows you how silly this was as physics. It's just junk. One stupid clay experiment. Terrible. Horrible. Awful. Terrible science. And here you are defending it. And then telling me you have integrity and you're preserving the truth and honor and decent. No, you're not doing any of that stuff. You're sitting here denying something that's just overwhelmingly one-sided in the evidence. The evidence is overwhelming that momentum is a fantastic formula. And the 1/2 mv squared is a paradoxical pile of rubbish. Oh, I should do the ending. Yeah, I forgot that part. Alright, so this has been a Draft Science video presentation. Such.